Okay, today we're going to look at estimators. Well, in this lecture, we're going to look at estimators for proportions. And proportions are probabilities. And so we've been using the variable p is the probability of success of a probability experiment for a single trial. We also had its related variable, which is q, is the probability of success. Sorry. And q is the probability of failure. And so if we have some population and there's entries in here, we want to know the probability of success or failure, or the percentage of something that we might see. And so what we can do is we can take a sample and we can estimate it. And so the point estimate for p, we'll write as p hat. And that's the number of the thing in our sample divided by the number of samples. And so this is the relative frequency of the parameter that we are not the parameter. Yeah, the parameter. No, the statistic that we were measuring. Parameters are in populations, statistics are in samples. And so if this was composed, let's say this is composed of red dots blue dots and yellow dots in some large number, but there's some proportion that each dot has in the population. If I take a sample and grab a sampling of this space, the proportion of the red dots to the sample should be an estimator for the proportion of the red dots to the population. And so what we're kind of saying underneath it all is my sample's proportion of red dots, we'll say here, should estimate the population's proportion of x red over the number of n, right? Try to count all the reds. And again, it's an estimator because our sample isn't a survey, doesn't grab every piece of data. But if we have a large enough number of samples, this becomes a good estimator. And so we're estimating a percentage, not an individual mean, which means we're looking at our space slightly differently than we did with the mean. Well, we can say then that our estimator for failure is 1 minus p hat. Because the probability space, there's either success or failure, we've made it binomial, and the complement of the probability space is 1 minus p. And so failure is always 1 minus the success, and success is 1 minus the failure. Sometimes you know one proportional value better than the other. And so what we want to do is look at an example of a proportional. So let me pull my example up here. You're going to see its solution and I'll walk it through. This is off one of the slides. I think I am here with my slides. And so let me bring this over here. I messed up a little. I'll fix that in a second. Let's see here. Trying to get my pen working on this screen. Yeah, there we go. All right, so if we look at this data here, we can turn this into an idea of what we're doing with estimations. And so the idea is we take a survey, and in the survey, so this isn't the population, 1,550 adults. 1,054 of them said they use social media, Facebook. And so we want to find a point estimate for the population proportion. We want to be able to say that this survey talks about the population. And so what we can do is we can take the 1,054 and divide it by the 1,050. And that gives us an estimate. Of our survey, 68% of the people said they used Facebook. That should be a good estimate for what the population is actually doing. And so this is what we mean by an estimator, is what we have measured in the sample should be telling us something about the whole. And so we want to be able to work that through. Well, then the other thing we need to do is find a confidence interval, because point estimates on their own don't really tell us much. If I know 0.68 is the proportion of the Facebook users, how confident am I that it's that value? What if the population is 0.71 or 0.65? Are these good estimates also? And so we want to build a confidence interval around our point estimate. And we do this in a similar fashion to what we did for the mean. But what we're going to use is so apologize for my dog here. What we're going to do is we're going to use some things that came out of the binomial experiments. And so what we want to do is be able to write that the true population proportion that we're trying to measure is going to be our estimate plus or minus some error. Now again, in the book will do this as your estimate less than the true population proportion, your estimate. Alright, it does this inequality. I like writing it this because, as you can see, there's the minus portion of it and there's the plus portion of it. And we get this range built in. This is just the notation I grew up with. Your book's going to do it this way. And so this is the population's proportion is wedged somewhere in between these two values. But what we need to do is we need to figure out the error. And the error comes nicely from the standard deviation and the mean formulas from the binomial theorem. And what we can say is, if we choose a critical value, so we choose some confidence level and its critical value. So we have a confidence level, and let's say like 0.95 or 95% confident. Then we choose the Z critical that goes with that. Remember, the tables are in the book. This would be 1.96. And so the error on either side of this is the critical value times your estimated chance of success times your estimated chance of failure over the number of samples you've taken. And then you take the square root of the whole thing. And this is kind of hidden in how we do the standard deviation for binomial experiments because of the chance of success and failure. And so this generates our confidence levels for us. Or confidence interval, I guess, confidence level, confidence interval. So let's come through here and let's do one here. So if we take that 0.068 that we got from the experiment of US adults, let's do that to a confidence level of 95%. Now, this formula works if a really weird thing happens. And I always forget to mention this, because I do statistics with stars, so I rarely have small n values. But this formula and this being an estimate will only work if n times q is greater than or equal to 5. Or no, sorry, yep. And n times p is greater than or equal to 5. And what you'll find is if p and q are near 50-50, it doesn't take a large n for this to happen, right? If this is 0.5 and that's 0.5, 0.5 times 0.5 is 0.25, and so you need an n of 20 for this to be true. And so I rarely check my n's on this, but again, I'm used to doing statistics with a million pieces of data, which it takes a very large separation in P and Q. You would want to start to worry if your n is drastically below 20 and your P and Q are widely separated. Like if you have like a 0.9, which would give you a 0.1 for the other, because that gives you a 0.09, and then n for your n to get 5, you're on the order of, let's see, that would have been up one more, 0.1, n equals 100, right? So you're on a high order of n. But this is the check we want to do, that n times q is greater than 5 and n times p is greater than 5. You'll find in most cases it's there. So if we go back to the statistics we did with 1054 adults, let me scroll up. 1054 adults, and 1550 was on the survey. So 1550. I'm going to use FB, and this was how many were surveyed. This is the proportion estimator we got from that when we did 1054 by 1550 was 0.68. And so we're thinking of the population, about 0.68 people use Facebook, but we want to put a confidence level to it. And so we want to say we want to be 95% confident. And so we're going to restate this. And so what we need to do then is figure out Q, which is 1 minus 0.68. So 1 minus 0.68 is 0.32. And so our error is going to be the critical value of 0.95, which is 1.96. So again, I'll rewrite this here. P times Q divided by N. I hope you can appreciate that just visually looking at 1500 times 0.32, I know that's bigger than 5. And 1550 times 0.68 is bigger than 5. I don't have to calculate it out to see that it's bigger than 5. If I have 60% of 1,000 things, I know I'm going to have more than 5. So I'll put the 1.96 times 0.68 times 0.32, all divided by 1550. I'm going to grab my calculator here. That's about 0.703. 0.703 is my error. And so I could estimate, well, we got 0.68 plus or minus 0.703 would be my estimate for the actual population value. Or if we do the mathematics on that, the lower bound is 0.657. If I subtract 0.703, that's the lower bound. And then in my upper bound, if I add 0.703, did I get that right? 0.703. Oh, no, I messed up. Hold on here. I'll do it quick. This isn't 0.03. That's the upper bound. Sorry, I added everything in my calculator beforehand. If you do this on the calculator, this is 0.023. And when I add 0.023 to 0.68, I get the 0.703. This is why I have to do this live sometimes. I can catch my calculator mistakes, or in this case, reading my notes oddly. You know, you always go back and double check my calculator when I'm reading off my notes, and I was reading the wrong column here. But so this, you plug this in on the calculator, and you get 0.023, rounded to 3 decimal places. If I add that to this, I get 0.703. 23, there we go, fix that. And if I subtract it from this, I get 0.657. And so I have made a confidence interval for a proportional statistic. And that lets me talk about, I'm 95% sure that the number of adults that use Facebook are between those two percentages. And if I read those percentages out to you here, it's 65.7% and 70.3%. And that's a better way to talk about our statistic than the point value itself. Because we are not fully certain, we have to state how confident we are. We're 95% confident that our mean lies within there. And then we can do a similar thing that we did with confidence levels, is we can find the minimum sample size we want. Now, a weird thing about proportions is we don't know what the percentage is going to be when we design an experiment, but it is a fair assumption without any knowledge of the system that most chances of success and failure are going to be around equal. And so that it's going to be 0.5 times 0.5 for the P and Q. And so if we use this error function and we want to get within a certain percentage, and we need to know how many things we need to do that, we can reverse this process. But what I'm going to do is I'm going to replace P and Q with that we're close to 0.5. We're close to 50-50. Without any assumptions of what we're going to get in the experiment, we suspect things to be 50-50. If our model tells us otherwise, we can update that. And so I'm going to do the same arrangement here. I'm going to divide how close I want to be in percentage by the critical value. I'm going to square both sides. And now I'm going to cross multiply. I'm going to bring n over here. PQ is still going to stay here. And at this point, I'm going to replace, I know multiplying P by Q is going to be 0.25. So I'll put 0.25 here. And then I have my critical value over the error I want. And for those of you who are used to fractions to decimals, that's also 1/4. So whatever this value is, we take 1/4 of it. And that gives us the number of things that we would want to run in our experiment. Based on how close in percentage we want to be when we drive that error. Right? If we want to be closer than 0.023, we want to be closer than 2%, we change this. And then we say, well, we need more survey things. All right, that's point estimate and confidence estimates on proportion. And you should note that it parallels very much what we did with the mean, where we get a slightly different error function, but the ideas are the same in laying out the space.